this quickly. We'll go to the what is called as precision operator. So this is C2V we are taken, water molecule. So the axes are XYZ. I define like this. This is for E. This you must know very much. So C2 along Z axis if you rotate, what do you get? You rotate along Z axis C2. The coordinates, the Cartesian coordinates. We are just following the Cartesian coordinates XYZ. We can write x becomes -1, 0, 0, 0. Y will become -y, 0, 0, and z will remain as z. And then similarly, we can write for sigma v prime, 3 by 3 matrix. So if we cut the molecule into 2, y will be interchanging it. No, y will change its sign. 0, 0, 1, whereas sigma v double prime if I use, x will change its sign. That's it. 0, 0, 0, 1, 0, 0, 0, 1. Okay, so now we can write the character table. We have P, C2, say z-axis, sigma v prime, what we are considering, xz-axis. And then sigma v double prime, yz-axis. So this is what we have basic information, right? And also we studied some properties of a character table, that number of classes equal to number of irreducible representations. If you recall it, number of classes equal to number of irreducible representations. In water molecule, if you work it out, there will be 4 classes. Each operation is a class by itself. So you have 4, this one, I call it as gamma 1, gamma 2, gamma 3, and gamma 4. We don't know, right, which one is what. So we just list it out, all 4. And then, so from the Cartesian coordinates, we can see, I mean, there could be only 3, right? So 3 we can define. So from this matrix, you can write, so this is x, y, z. So for E, x is 1. For C2, x is -1. For sigma v prime, x is 1. And then sigma v double prime, again x is -1. So this is first one. Again, similarly, you can write, see the second row. For E, it is 1. For C2, it is -1. For sigma v prime, again -1. Sigma v double prime, it is 1. So you can write like this. Third one also. So I can write this is for x-axis, this is y-axis, z-axis. Let's see for z. Z is, it is 1. Sigma, okay, C2 z, it's again 1. Sigma v prime, again it is 1. Sigma v double prime, again it is 1. So all 4 are 1. So this is z-axis. So last one, we don't know what is what. So I write this one as A, B, C, D. Okay. So we want to find out the 4th IR. Its characters. Okay. So how do we do that? So you know these IRs are all conjugate to each other. I mean the IRs are all orthonormal to each other. So we apply the orthogonality. So you take the product of tau 2, 1, tau 2, I mean the gamma 2, 1, gamma 4. So it's orthonormal, okay? All the IRs are orthonormal. So you take the product, gamma 2, 1 and gamma 4. So if you take the product, there is a formula, right? So if you take it, it's 1 over 4. And then 1 over 4 is coming 1 over h. Yeah, h is number of elements in the group. It's an order of the group. So you can write like this. Really do need it. 4. It's not needed. This is not needed. Orthonormality is not needed. Just the product of 2. So basically, if you see the big orthogonality theorem, you find this multiplied by this. This is what we are doing it. If you do that, gamma 2 and gamma 4. So it's A what A into you can say what. So I just so yes, it's minus B. Then this into this minus C plus B equal to 0. So this is the property we consider gamma 2, gamma A. If you take the product of N into IR, it should be equal to 0. So this is gamma 2 and gamma 4. So we can write A plus B is D equal to B plus C. Am I right? Gamma 2 is okay. Maybe I've taken a wrong combination. I can take something else combination. So this is 2 and 4. Now let me do the other one. You can get this also, but let me do as in my notes. Let me just do this one more time. So considering the orthogonality, I'm just taking the product of gamma 1 and gamma 4. Okay, so that should be equal to 0. So let's consider that. So this is A into 1 plus the summation. Summation over gamma 1, gamma 4. So A into 1, B into minus 1 plus C into 1 plus B into B minus 1 equal to 0. So this is A minus B plus C minus D equal to 0. So A plus C equal to B plus D. So this is one relation I get. Similarly, take the product of so 1 and 4 you're done. 1 and 2. 1 and 2 is what? 1. 1 and 2. If you take the product, what you will get? So let me write it here. Gamma 2 should be equal to 0. So I'm just taking the product of IR 1 and 2. Okay. So applying the great orthogonality theorem. So 3, 1 and 2. No, 1 and 2, 1 and 4. You have done 1 and 4.
So I think we have to multiply gamma 4 to all three remained.
Let me check 2 and 4. 1 and 2 will be 0. Yeah, so if you take the product, I think 1 and 2 will be 0. So it doesn't matter. We want to see this relation. So 2 and 4, if you take, what do you get? A minus B and then minus C and then plus D equal to 0. So this will be A plus D equal to B minus C. I'm multiplying the wrong one. So I want to get B plus D. Okay, there you go. Let me check. I'm just multiplying the wrong one. So T2 and gamma 2 and gamma 4. It be 0. So gamma 2 is minus B. Okay, minus C plus D equal to 0. So we can write this as again, we're getting the same thing, right? Here also again we're getting the same one. A plus D equal to B plus C. So this is different. A plus D equal to B plus C. But take something else. 2 and 3 and 4. Let me do 3 and 4 also, but this is all going to be positive. I'll do gamma 3 and let it be like this. Gamma 3 and gamma 4. Let me do this. It should be 0. So it is A plus B plus C plus D equal to 0. So A plus C equal to minus of B plus D. Okay, so here, see, so this is one relation, but we are not using that. But if you multiply gamma 3 and gamma 4, these two, you will end up with A plus C equal to minus of B plus D, whereas here A plus C equal to plus of B plus D. So it is not matching. So for that purpose, what it means is A plus C has to be 0, which implies A plus C has to be 0. Because two different relation you are getting. Here it is plus of B plus D, whereas here it is minus of B plus D. So that means this left hand side should be equal to 0. A plus C equal to 0. So you write A plus C equal to 0, right? So A will be minus C. This is possible only when A is 1 and B is C is minus 1. Then only it becomes 0. So this we can write A as plus 1, C as minus 1. Okay. And similarly, you can get the other relation also. We got B plus D, right? So again, you put B plus D equal to 0. So one should be negative, one should be positive. If you consider that as the relation, B plus D equal to, let me check, B plus D equal to 0. So what we are doing is A plus D, A plus C equal to B plus D. So if you substitute here, minus B plus D. So no. So B also should be 1, and then C, D should be minus 1. No, I'm not getting this. So let me check. So this B equal to 1, D equal to minus 1. A plus C. So how it is explained is, since you are getting this relation, so here A plus C equal to B plus D, right? So A plus equal to B plus D. So we write again A plus equal to minus of B plus D, which is also we are finding out from A plus C here it is B plus D. So since this is it's not possible, so what we have to do is you have to equate these both. A plus B equal to 0, B plus D equal to 0. So what it means, A plus C equal to 0 and B plus D equal to 0. So when you do that, it's only possible when you have A is plus 1, B, C is minus 1, and again B is plus 1, C is, D is minus 1. Like this, one can write. So in this way, it is using the orthonormality property of two IRs, you take the product and equate it, and somewhere it is not matching properly. So then that means left hand side should be left hand side and right hand side should be equal to 0. So from that, get cancelled out, right? So it's all 1D. So it's a one-dimensional representation, right? So it's all could be 1 or plus 1 or minus 1. So that's why it is A is plus, C is minus 1. Again, B is plus 1, D is minus 1. So like that one can write. So if you erase this, so we got 4 IRs. And there is a notation for each one, right? So it's all 1, 1, 1, 1. So it is called as A1. And then 1, 1, minus 1, minus 1. It is what, A2, and then we have 1 minus 1. So this is B1, 1 minus 1, 1 minus 1, and then last one is B2. So like this, it has been constructed. So all the character table generally uses this property, the orthonormality. They are orthogonal.
Hello, sir.
Yes, yes, tell me.
Sir, in case of B and D, we can also take B equal to -1 and D is equal to +1.
You're saying B equal to, I mean, this as -1, C equal to +1, right? Other way.
Yes, sir.
+1. Find out we can take. Yes, we can take. In principle, we can take -1. Let me check now. I never tried this. Let's do it. The other properties also. Okay, I just call it as prime. So +1 is -1. B is say +1. C is +1. Okay, -1. So you're saying, yeah, it could be other way, right? This is -1 +1 +1 -1. So if you,
Hello, sir.
yeah, it was A, B, C, D.
Hello, sir.
So I'm just changing. But if you do that, the property may not be valid. You know, so E, it should be +1 only, right? In E symmetry, it should not change sign. I mean, when it started with 1, it cannot change it also. So this column has to be always positive.
Hello, sir.
It is not possible. So A has to be positive.
Hello, sir.
Yeah.
Sir, A and C is fine. I'm asking about B and D. If we take D is equal to -1 and D is equal to +1.
Okay. So +1. Let me try. So A, B. So this is -1. Is already -1. It is +1. Okay, like this, right? 1 -1 -1 1. Right? If you take B, this is as B, and this is D. But this one is already present, no? So if you see 1 -1 -1 1, so 1 -1 -1 1. It's already there. So if you see every row, it will be unique in a character table. It cannot be same. I mean, that cannot be any repetition.
Okay, sir.
So other possibility is it has to be +1 and this has to be -1, which is not there. Yeah, so that's why we have taken this one. I mean, both the we have to work out the possibilities, and then when you substitute it and then see which is not feasible, you take it out, and then we are taking this one. So B is again +1. So A and B are +1. C is -1 and -1. Okay. I mean, if you have to put it in the character table and see whether it is fitting or not, then we have to assign it.
Okay, sir.
Okay. So this is about the construction of character table. And similarly, I mean, here you see we have written the translational vectors, right? T, X, Y, Z, the translational vectors. Similarly, you can find out the rotational basis also, what basis it is coming. So this is okay. So where is RZ will come, where RY will come, RX will come. So that we can write it. So for example, saying water, say it is Z, we have considered this axis, right? Z axis. So if it is rotating clockwise, and if you use this operation E, it's not going to change, so it is 1. C2, if you rotate again clockwise, it continue to rotate, so it has to be +1. So it could be gamma 3 or gamma 4 if it rotates. And sigma V plane, if you place it like this, then it start rotating in anti-clockwise direction. So this will become -1. And then if you place a mirror across, then it becomes -1. So this one corresponds to RG. So this one we wrote it as, I think, what, A2. This is A1. This is B1 and this is B2. So we can assign which is RZ, what is RX, what is RY, like that. So we can fill the columns, all the columns. Yeah. So initially we start with XYZ transformation vectors. You can also fill where is RX and RY will go. You can check it. RX will go in B2. RX will B2 and this is RY will go here. So we have to follow the basis, the which. So this is Y, this is X, right? So you see how it changes, then we can find out RX, where is RX and RY go. So it goes in B2 and B1 respectively. So like this, one can build the character table, mostly considering the orthogonality of the IRs, and we can do it. Similarly, try for C3V. Okay. So this is we have done for C2V. C3V also you can work it out. C3V you will have how many? There are 3 classes, so you should get 3 IRs. And then you see the number of groups, number of what is the order of the group. So order is H. Order H is 6. So when it is 6, when it's 6, then you have to use the properties summation over chi square or dimension Li square equal to H. So it could be what character it could be. So it's 1 plus 1 square plus 1 square plus. So H is 6 in this case in C3V. So 1 square plus 1 square plus only possibility to do it 6 is you have to make it 2 square. So it's 1 square plus 1 square plus 2 square. So then it becomes 6. That's why you get what A1, A2, and E. So because this is 1 dimension, this is 1 dimension, this is 2 dimension. Yeah, so it has 3 classes. That's why you're getting 3 IRs, and 2 are 1 dimension. Third one is 2 dimension. So this was C3. So you can build it like this, and then you take the product of A1 means all positive, right? So A1 is all positive. Whatever it is C3 2 times and then 3 times of sigma V. So it's all positive. So you know 1, other 2 you can find it out. So you work it out, use the different properties. Say you say XYZ, and then you take the product of A1 and A2, and then you find out what is XYZ. And after finding out 2, and you go for E. Okay. For E, it is a 2 by 2 matrix, but I suggest you try it. Okay. So this is all about constructing the character table. Any point group given, you can construct it with the existing knowledge, with whatever you have learned in few classes, last 10, 11 classes. You can try. Okay, so now let's go to next part. What is called as projection operator. So if you see in books, no, it will be written. We'll use this projection operator in studying the symmetry adapter linear combination of orbitals. It's called as SALC orbitals. So main aim is to find out the symmetry of the orbitals. So if you use this projection operator, one can easily determine the symmetry of a given orbitals or any function, orbital functions, vectors, any other given function. So this is very handy, this projection operator, to find out the symmetry. Basically, to find out symmetry of orbitals or bonds or functions. So this is given by a term. So it looks complicated, but the operation is very simple. So this is P with the superscript gamma. Gamma is the IR, right? Then it is Li by H. So Li is the dimension of the IR, and H is the order of the group. And then it is obviously it is summation over all the operations. All the operations. Chi I. Okay, chi operator, and then this okay. I'll explain the terms what we are using it here. So P is the precision operator. In the superscript, it is the IR, the corresponding IR, and you know these two terms. It's a dimension of that IR, and H is the order of the group, and sum over all the symmetry operations multiplied by chi into O. So chi is basically character of operation. Chi is the character, right? Character, and then superscript is the corresponding IR, character of the IR. 0 is for I do it like this, and then O. O cap is again operator. O is the symmetry operator. So this is symmetry operation. So this we know it's a character of IR. And then this is a precision operator. Of corresponding IR. Okay, so this is the formula. The definition is basically an operator projects out a basis vector or a combination of vectors of a well-specified symmetry. So it basically just projects out the a basis vector or combination of orbitals of a specified symmetry. So that's a precision operator. I'll give you one example, then you'll appreciate better. So let's have it for C2V itself. Let's go with C2V only, simpler. Say we have a water molecule with, say, one orbital. So this is Y, this is Z, this is X. Okay, you have this one. Which orbital take? PZ orbital take. No? PZ orbital, so plus minus C2V. So PZ orbital we take, and then projection of which symmetry we take? Projection of A1 symmetry we take. So basically, we are trying to do. We project out PZ orbital with A1 symmetry. If you know, C2V is having E C2 sigma V double prime, right? So if you perform a px orbital, it remain as PZ orbital. It remain as PG orbital only, which is here. And if you perform C2, again it will be PZ only. If you project sigma V, again if you perform sigma V, it is not going to change. So it is PZ only. If you perform sigma V double prime also, it is going to remain as PZ only. So PZ will remain as PZ. So if you project out with A1 symmetry of PZ, this will be 1 over dimension all 4. So 1 over 4 into. So basically, what we are doing is multiplying with its character. So character multiplied by its symmetry operation. Symmetry operation. So it is 1 into. So it is say A1 is 1, 1, 1, 1, right? So we are just doing A1. So it is 1 into PZ plus 1 into PZ plus 1 into PZ plus 1 into PZ. So this is what we have done. So here it becomes 4 by 4 PZ. So if you project out PZ orbital in A1 symmetry, it results in PG only. Okay. So now let's consider P some other orbital. Let's try px orbital. Okay. So in water, say P, the projection of px orbital with A1 symmetry. Okay, so if you project out, let me see what is it. So we are using this formula basically. So it is 1/4 px orbital. So px we defined this axis, right? So now it is oxygen is there. So the z is, we can say the px orbital is coming out. So px is something like this. So I don't know how to write this. So this is you can imagine the px orbital is coming out of this board. Positive part is coming out and negative is going backside, you can assume. So if you use px with A1 E, under E it is going to remain as px only, and then under C2 px will remain as, you change it to you rotate, it becomes minus px, and then sigma v if you perform, sigma v is cutting this, it's not going to remain as a px, and then sigma v double prime. So if we use that, it becomes minus of px. Okay, so the orbital projection will be something like this for various symmetry. This is for E, this is for C2, this is for sigma v prime, sigma v double prime. So this gets cancelled. This will become 0. So projection of px orbital in A1 symmetry gets cancelled out. Similarly, you can find it out for B1 symmetry. Can you try and tell me what is for B1 symmetry? Projection of px orbital with the B1 symmetry. It remains or cancels out. So what is B1? One is.
Sir, it remains.
It remains, okay. Others? So B1 is 1 minus 1, 1 minus 1, right? So it's 1/4 px orbital. Again, this is coming out. So we can say this px plus minus 1 of minus px, right? So if you perform C2, it becomes minus px, whereas character of D1 is for C2 is minus 1. That's why I just want to be minus 1. Again, third is px. Here it is 1 plus minus 1 of px minus. Okay, so last px orbital, again in sigma v double prime, it becomes negative. So you can cancel it out. So it becomes 1/4. So px plus px plus px plus px. So it becomes 4/4 px. So it becomes px. So it remains. So if you use the px orbital in B1 symmetry, it just remains. It doesn't get cancelled out. So what it means is the B1 symmetry projects out the px orbital itself. Okay, so basically we use this technique to arrive at the symmetry of the given function or vector or combination of orbitals. Okay, so if you try with A1, it was giving 0, right? So this we call it as the projection of A1 annihilates px orbital. So projection of A1 symmetry annihilates px orbital. So because it gets cancelled out, 0. So projection of A1 annihilates the px orbital. So if it gets cancelled out, then we say it's annihilates. If it remains only one time, that could be two times also. When it comes off like that, then we say it is projects out the corresponding orbital. Okay, so we use this technique for finding out the symmetry. Maybe next class. Okay, so I will not giving any homework because you have a quiz on Wednesday, right? So today's part is not included. Don't worry about today's part. At least projection operator don't include, but other things are included. So it's for 20 marks. It's for 1 hour exam. I think I sent an email, I think, right? Most of you got it. I think you might have seen it. It's at 2 o'clock. You should be getting the paper by 1:55, something like that. You download it and then start working on A4 sheet and then scan it by using any app. If nothing works, you scan it as an image and save it as PDF. And then you just, in the Google Classroom itself, you turning. There is an option called turning under assignments. So you turn in it, and then I get the answers. Okay. By 3:05, I think I have given a time, I think, right? 1 hour exam. So by 3:05 p.m. you have to turn it in. Okay. So any question on that? I don't know what happened to others, but those who are awake, quizzes on Wednesday. Okay, so I got a lot of queries from students. I try to answer whatever possible. I am still going through a lot of queries, so I'll just solve it and send it. Not everything, but at least whatever I could do it, I send it. But you will get it.
Sir, I have also sent a query regarding group multiplication table.
Sorry, can you
I
repeat?
Sir, I have also sent the query regarding the group multiplication table.
Yeah, C3V, right? There's no
Yes.
problem. I think I worked out. It is fine. I mean, your question is if you multiply right side to left side, right?
Yes,
Or
sir.
left to right side. See, group multiplication table, you have to multiply only 2 times. I mean, the C to C3V. So you have written a lot of things. B, C3, E3, 2, sigma V prime, double prime, triple prime, and then you have again the same things. B, C3.
Sir, the board is not visible.
Board is not visible. Yes, not visible. No, I'm answering who has asked questioned. I didn't find some. So first row and second column is fine. So this is E, you get it. This is C3 2. This is C3 into C3. So I don't want to rewrite everything. But what I'm saying is to multiply it. If your question is if you multiply sigma V and then C3. So what you are going to get, and then your question is if I multiply other way, C3 sigma V prime. Both are different. That's your question.
Actually, board is not visible. Can you repeat?
Not visible.
But it's not clear.
Okay, so I write it here. So your question was if you multiply sigma V prime and C3, you're getting one answer. What you will get? So you will get C3 into C3 is E.
So my main question.
I would say you will get double prime. Are you getting that?
Yes, but
And
when
here
we multiply.
V triple prime. So your question is this will get sigma V double prime. Your question is if you interchange it, it's different, right? That's your question.
Yes, sir.
So I'm doing C3 into sigma v. So I get sigma v double prime here also.
It should be different as it is a non-abelian group, no?
Yeah, they are non-abelian. No, these are non-abelian, so it will be different only.
But when we when we multiply the two terms by its inverse, for example, in first example, if we multiply the whole term by C3 inverse, then we get the same result from the two results. Sigma v. No, no, no.
What do you multiply? C3 inverse.
Yes.
No, you cannot multiply. It's two different things, no?
Sir, I have sent a proper by writing them in a PDF form.
Now I will go through it. Who is it Robin or Prince? Who is
Karan.
whose question is this?
Karan. Karan. Yes, sir.
Yeah, I'll take a look and then answer to you. Okay. So as such, that's no problem. I think you see this will be different, of course, because they are a non-abelian, so it will be different. I'll answer to you. Okay. I'll send by reply by tonight. Okay.
Okay.
See your query. What is because you are taking product of three. I'm concerned. Inverse sigma v inverse. If you do that, it should be.
Yes, these are the different answers only.
This is different. You should get in C3 or something. C3 or C32 you'll get.
But in my problem, the three are same only.
All three are planes.
All three are same. Like C3 inverse, sigma v, and C3.
Sigma v and what?
Wait, sir, I bring copies. That copy.
What? Fine, I'll reply to you. Okay, fine. Okay, I'm not getting it.
Yes. Yes, sir.
I will go through it because you have sent two attachment. No, first attachment again another email you have sent another attachment. But as such, I can fill this. There's no problem here. Prime sigma v prime sigma v double prime. Here also I can fill this. So sigma v triple prime sigma v. There's a sequence you can say 1 2 3 2 3 1 3 1 2. So that's a cyclic thing is going on. So it's 1 sigma v double prime. So another things are C3 you'll get it here. Sigma v to sigma v, I think you're going to get E. So like that you can fill it. I mean, it's all sequence, you can do it. I'll take a look about your query and then answer it, okay? Karan, okay, fine. Okay, fine. Any question you can always send by email. I'm trying to answer most of it.
Sir?
Yes.
Sir, in previous class you taught about in-plane and out-of-plane concept.
What concept?
In-plane
In-plane, out-of-plane. Yes, yeah. Orbital.
Yes. Sir, I was not able to understand it completely. Like, what type of question will come from it?
No, it's basically say we consider the thing BCl3 molecule. In that there are PZ orbital and also PX or PY orbitals. So PX and PY are in-plane orbitals. PZ is the out-of-plane orbital. So we wrote the reducible representation separately for PZ orbital and PX and PY orbital, which are in plane. And then we just studied how the bonding is possible. For the sigma bond, it is PX and PY, and whereas for pi bond, it is PZ orbitals involved. So by studying this, by using the group theory, we found out PZ orbital is PZ orbital is pi bonding forming, whereas other two PX and PY along with S orbitals or sigma bond formation. So that's the only message we get from that exercise. For that, we wrote the reducible representation. Then we brought it to IRs, right? Different IRs. How many IRs are present in each, and then its corresponding symmetry we saw. And then based on that, we just wrote the bonding. That's it. So what type of questions? It's kind of which type of bonding will be involved. That can be found out by doing this exercise, by considering the in-plane orbitals and out-of-plane orbitals. Okay.
Okay, sir.
Okay, the paper may not be very difficult, but it will be lengthy. That I can assure you. The paper will be lengthy. You'll not have time to discuss with your friends, or to search in your notebook or whatever. But it will be a lengthy paper. Within 1 hour, you have to finish. Attempt as many as possible, and then send it back. Okay, and it'll be simple only. No, don't worry. It's the first quiz, so it will not be very difficult.
So we have to send it through email.
No, I sent an email. I think you have to. There is a Google Classroom in your Google Gmail account. You go there. In that, there will be something called assignment. In that, you click that, and then you return that. I mean, you upload the answers. You upload the scanned copy. Okay. So learn it today. Just click the Google Classroom, and then see where the assignment is located. There you have to upload it. If nothing works, you are most welcome to send it by email or WhatsApp. Okay, before time. Only thing is you have to send it before time. Either way, you can send it. Best thing is Google Classroom. If not, you send it by any other way. Okay, so all the best. Any query you can ask by email.